C03 representing cohort 3 group 9. So for our first task, we needed to predict the death rates for the different countries due to COVID-19. So importing the libraries we need for a project, we also need to read the CSV for the whole COVID-19 data. We decided to split the data into the 5 different distinct continents. So what I did is that I actually went to the website, then after that scraped out the relevant ISO codes. So from there we are able to split the data into the 5 different continents. Next, I also needed to export the data to Excel. So to prepare the exportation of data, we needed to average the data for each continent based on the dates. So after getting the feature variables, we decided to compare the relevancy of the data for each different continents. Looking at the pair plots, we can see that some of the data are actually scattered and some of the data are also underreported or not reported at all, as seen from the African continent and also the South American continent. We decided to go for 2 feature variables that were most relevant for all continents. The first one being new cases moved and the second one being people vaccinated. So with the new chosen feature variables, we needed to prepare the data for normalization and also getting the beta values as well. So from here, we decided to use the closed form equation to find the minimum beta values. Okay, afterwards, we used 2 different metrics to compare the accuracy of the data. First one being mean squared error, then the second one being adjusted R square. So using line plots, we were able to compare and see the trend for the predicted Y value and the actual Y value. Seeing that we can improve the model further, we decided to add in one more feature variable. So with the new feature variable, we did the same thing as before, and after that drew a line plot. Okay, so from there you can see that there's an improvement in the model. So what we need to do now is to do the same thing but for all the other continents as well. So what we need to do is extract out the data for the feature and target variables, convert them into NumPy arrays, then normalize the feature variable. Afterwards, calculate the minimum beta values using a closed form equation. Then after that, calculate the predicted target values. Then lastly, getting the relevant data frame to plot for the different continents. Afterwards, I use a subplot to visualize the graph for all the regions and also create a data frame to include all the relevant beta values and also the matrix. Next, I'll be passing on my time to Kavri to talk about task 2 and the web app.
In task 2, we decided to focus on how we can help people in this pandemic. And through our task 2 and the web app, we'd like to help in predicting whether or not someone may have COVID based on some preliminary symptoms. And essentially, we'd like to build a logistic regression model that helps in binary classification. So we got our data set on Kaggle, and our data set has 21 columns, which are our features and also symptoms. And we have a lot of rows in our data set. So let's get into it. We import data, we load our data, and then we look at the shape of our data set, what kind of objects are in our data set, what kind of columns are in our data set, what are the names of our columns, how do you describe them, and all of that. So now that we've gotten familiarized with our data, we then look into data preparation and data cleaning. So we look into the number of missing values in our data set and the percentage of missing values in our data set, and then we go on to do some cleaning, and then here we look at how many positive and negative COVID cases are there in our data set, and this is a much better representation of the same statistic. And these are not other count plots that basically tell us whether someone had COVID or not, given that they had a particular symptom. So these count plots have 20 of these count plots because we're not counting the COVID-19 feature, which is our target variable. So from these count plots, we can see that there are explicitly high levels for some of them. You can see the stark difference here: breathing problems, fever, dry cough, sore throat. And now we get to feature selection and target preparation. So we have one hot encoding, which is essentially, we use it for categorical representation of data. We convert all our yeses and nos to ones and zeros, and then we represent them in the form of a histogram. We look at what kind of correlations they have, and it's a proportion of whether or not someone has had a particular symptom in our data set. And we look at all our columns, and then we drop all the features that we're not selecting. So now the features that we are selecting are breathing problem, fever, and dry cough. So we essentially chose these features because they have the highest explicit correlations in our data set. And since we're starting out, we started out with 3 features. And now we're building our model. We import libraries, we build scalars from scratch, we split the data, we run the logistic regression function as a class with multiple functions inside of it, sigmoid, cost function, fitting the model, prediction, and then our X is essentially all our features except COVID-19, and COVID-19 is our target variable, which is why we split the data, we run the model, and then we predict it, and now we get to evaluate the model. So we build our confusion matrix, true positive, true negative, false positive, false negatives. We go on to our accuracy, precision, recall, F1 score, mean absolute error metric, and then we print all of these, and then we can see that our accuracy is actually decent, but it can definitely be greatly improved. Our precision is also less, but recall is relatively high, so there's lesser scope for improvement. F1 score can also be increased, and these two can definitely be decreased. Our misclassified samples are quite a lot, so that is something we'd like to reduce as well. Absolutely, our error as well. And this is a graph that plots logistic regression training of epochs versus the loss function, and you can see it gradually decreasing. Now that we have our initial model, we'd like to improve our model, which is why we'd like to build correlation plots. And these 3 are feature importance plots of our features that we took in our initial model. And we build heat maps for our correlation. The bottommost row and the rightmost column are of more importance to us. And then we look at these gradients, and the ones that are important to us are the ones here. And the ones with the higher correlation hold more of interest to us. And if we set our threshold at 0.35, which is what we did, we can have all our features chosen that way. And then we choose our features, we drop everything else, and then we go through the same thing, we run the function, and then we get our metrics. And then now you can see that our metrics are actually so much higher. The accuracy is increased by 6%, precision is increased by 7%, recall, like we had already thought about it, didn't have much scope for improvement, but it still increased. F1 score also increased by 3%, which is really good. And our misclassified samples have actually decreased by 100, which is great, and we'd like to believe this is because we tweaked our parameters, feature selection, train test split, proportions, learning rate, epochs, all of those mattered. And these are the this is the feature importance plot of our final model's features. And this is again a logistic regression training plot of the epochs versus loss. And now to discuss, our initial model, we had 3 features, which were fever, dry cough, and sore throat. Our accuracy was less, a lot of our metrics were less, and number of misclassified samples were more. So we tried to tweak parameters, and then we ended up with a higher F1 score, higher accuracy, higher precision, higher recall, and a lot of good metrics. So overall, I believe our results were a good increase from our initial model. And in conclusion, with our improved model and features, we believe we'd now be able to classify whether or not someone has COVID-19 or not with a reasonably good accuracy, which is around 76%. But however, we do acknowledge that there can be flaws in our models. So as we learn to live with the virus, various governments around the world are adapting to the circumstances that are going on, and there could be inaccurate reporting of data, and our binary classification model doesn't always account for mutations in COVID-19 virus, which could lead to different kinds of symptoms in different people. So that's task 2.
So this is our web app. The main aim of our web app is to help users indicate whether or not they have COVID-19 based on their preliminary symptoms and to advise further steps for them. So over here, you can actually navigate through the page by clicking on the links at the top of the web page. So by clicking on COVID-19 scanner, right, you are able to predict whether you have COVID-19 based on the different symptoms you have. For example, breathing problems and dry cough. So from here, when you click on chat scanner, the web page does is that it actually links to the logistic regression model that we built and help you predict whether you have COVID-19. Afterwards, you can click on the COVID-19 scanner again. And over here, it seems that I have contracted COVID-19 and they advise me to actually look out for resources or reach out to them. Then as you scroll through, we have basic infographics of COVID-19 symptoms and also how it spreads and also how we can prevent COVID-19. That's all for our web app. Thank you.